Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping, and you're stuck with me once again for today's episode. I'm going to be starting another sensor series here. I've done this in the past where we talk about specific sensors on a vehicle or specific components on a vehicle, but this is all going to relate towards inputs or sensors. Most of the time, these are going to be related to the engine control module, but we see these used in multiple other areas of the vehicle as well. The next three that I'm going to be doing, and I'll just do one today, and we'll do the two others in following weeks, but the sensors that I'm going to be covering are speed and position sensors. Okay, so these would be like your crankshaft speed sensors or your camshaft position sensors, right? Speed and position does both. But these are for rotating components, components that spin a full 360 degrees. We have to have specific sensors in order to monitor the speed of that rotating component and, in some cases, the exact position of the rotating component, right? If we're doing a wheel speed sensor, for instance, a CV axle with a tone wheel on it, we may not need to know the exact position of that wheel in rotation. We're more concerned with the speed of the wheel, right? But something like a crankshaft or a camshaft, we not only want to know the speed of said rotating component, but we want to know exactly where it is in rotation. So these sensors can provide both those pieces of information, but there are various sensors that can do this. So I'm going to break this down. The three sensors that we'll talk about one at a time. First one's going to be variable reluctance. That's what we're going to talk about on today's show. Then I'll cover Hall Effect sensors, and then we'll do Magneto resistive sensors as the third episode in this series. So once again, today we're going to cover VR or variable reluctance sensors. I've also heard these classified as permanent magnet sensors, or even just a pickup coil would be the other one. That might be the older term that was used. See these a lot in distributor vehicles, right? It's just a simple 2-wire sensor plugged into the distributor, used as a, I don't know if you call it a crank or a cam sensor, kind of does both because you're spinning off of the camshaft on a distributor vehicle. But either way, we're, again, monitoring engine speed and position through this sensor. But I'm going to refer to them as variable reluctance sensors, and we're going to talk about exactly what these things are. If you're not familiar, you may be very well familiar with this if you've been in the automotive industry for any amount of time. But we'll talk a little bit about the diagnostic side of these, the operation of these sensors, and just things you need to be aware of if you're going to be working around or with these sensors, some stuff that can help you out and avoid some pitfalls. So we'll get into the basics of it here. This is really just, and they call it a permanent magnet sensor. It's really what it is. We got a permanent magnet, so just think north and south pole, and essentially there is just a fine coil of wire that's going to be wrapped around said magnet, and it's going to be housed usually in a plastic assembly that makes up the sensor, right? So we have a magnet and we have a coil of wire. That does make this sensor pretty simple and low cost. Also pretty reliable too. I mean, there's no moving parts in the sensor itself, right? There's a moving tone wheel, obviously, but in the sensor, there's no moving parts. And pretty basic to construct in comparison to some other sensors that might have an integrated circuit board in them. But that's really all this sensor is. So a nice part about doing audio only is that you can visualize a coil of wire that's going to be wrapped around a permanent magnet. Of course, the coil of wire is insulated from itself. So we essentially make a really long circuit that is coiled around this permanent magnet. Okay, so that's the construction of the sensor. Pretty straightforward and easy there. And so we're going to take this sensor and we're going to mount it close to the rotating component that we want to measure. Now, this rotating component, whether it be a CV axle, a crankshaft, a camshaft, whatever it is, it's going to have some sort of reluctor or tone wheel, which is just a toothed wheel. And these teeth that are going to be protruding off of the rotating component are going to be a ferrous metal, meaning that it is metal that will interact with a magnetic field, right? So think of a cast iron engine block. If you stick a magnet to it, the magnet sticks. Aluminum would be an example of a non-ferrous metal, right? So it's metal, but you can't stick a permanent magnet to it. So that's what I mean by as far as a ferrous metal teeth. They are just metal teeth that are going to interact or change a magnetic field when they're in close proximity to it. Okay, so we got a permanent magnet, coil of wire, close proximity to a rotating component with ferrous metal teeth. That's our basic setup. And again, most of you are probably familiar with how this is set up, but that is the basics for this sensor and how all of them operate. So the basic principle here is that there's already a magnetic field, if you will. And if you listen to the episode of Fonslow's podcast where we talk about magnetic fields, they don't really exist. But for the purpose of this explanation, we're going to consider that they do. There's magnetic lines of flux around this permanent magnet, right? Just again, think of a magnet, north-south pole. And if you've ever used the little metal shavings, you can see the flux lines for the magnet, right? We have that around the sensor. If you take this sensor out and you stick it to a piece of metal, it will stick, a ferrous piece of metal, because it is a magnet. And those lines of flux are already present around it. And we're just going to consider that a magnetic field. It's the easiest way to explain this. Now, as the rotating component spins, we have these metal teeth, these ferrous metal teeth, and they will move within close proximity of this tip of this sensor. What that does is that is going to interact with this magnetic field that is around the sensor, those magnetic lines of flux, and it will actually increase the size, if you will, or the strength of that magnetic field. It will change its dimensions. It will actually move this magnetic field because we're aligning a ferrous metal with this magnet and we're changing those lines of flux. We're moving them. That's the important part to know, is that there is movement of that magnetic field as the tooth gets closer to the tip of the sensor. Okay. Now, as the rotating component moves past, the opposite happens. The magnetic field is going to shrink, it's going to get smaller, but again, it's moving, it's changing in dimensions. And then the next tooth comes along as this rotating component spins, and then it goes back out and then back in and back out and back in. So essentially what we've created, and this is the important part of the sensor, is a moving magnetic field. Okay. And if we go back to basic electronics and induction, electromagnetic induction, if you think of an ignition coil, if we move a magnetic field through a conductor, like a coil of wire, copper wire, or we move a copper wire through a stationary magnetic field, you can do it either way. But in this case, or in ignition coil's case, we're moving a magnetic field through a conductor, right? With an ignition coil, we're shutting off current to a coil that we've built up a field, and we're allowing it to collapse in on both the secondary and the primary windings, which induces a high voltage into that secondary. In this case, we only have one coil of wire, and we're not trying to make a spark here, but we are trying to make some voltage. We are trying to induce current into that coil of wire that's surrounding the permanent magnet. So again, as this magnetic field is changing, it's expanding and contracting, we're moving that magnetic field across the coil of wire, which induces a current. And so all we have to do at that point, because we know we're going to induce a current from a moving magnetic field over a conductor, we're going to connect those two ends of the sensor to a control module, and with some circuitry on a board, we can utilize that information, right? The computer is basically visualizing the movement of whatever rotating component it is through the changing voltages that are created from the changing magnetic field, which is caused by the movement of these ferrous metal teeth, right? And so the faster that this component spins, whatever it is, the more often that we're going to have a change in voltage. And I'll talk a little bit more about the voltage that's induced as well, but that's the basics of the function of the sensor. Is we're using the movement of these metal teeth to change a magnetic field, which changes the voltage, and we're going to watch it, or the computer is going to watch it on the signal wire, and then act accordingly depending on what's being measured, whether it be a crankshaft or a camshaft. Now, one thing, a couple of things to consider actually is that this sensor does make its own voltage, right? Which is not true of every sensor. If you think of like a mass airflow sensor or a Hall effect sensor or a pressure sensor, those sensors don't create their own voltage. They're going to use a reference voltage or a supply voltage from a module or from some other source in order to produce a signal. And if they lose that, they can't do anything. This is a sensor that needs nothing except for that movement and change in magnetic field, and it develops its own voltage source. So you can almost think of this as independent from the rest of the electrical system on a car, right? You could disconnect, you could unplug one of these sensors and put your meter or scope on the end of the sensor, spin whatever component that is, and you'll get a sensor out, you'll get that output, you'll get that voltage or that waveform right out of that sensor. It doesn't need to be connected to anything. So just something to know if you're getting into it is doesn't require any reference or supply voltage in order to operate. Now, with that being said, there are some vehicles, there are some systems that will have a bias voltage going to these sensors. Okay. This is used for circuit integrity monitoring, not for operation of the sensor. So you'll have a DC constant coming out onto this wire, and then the computer is actually able to monitor the switching AC on top of that DC constant. If that doesn't make any sense to you, just keep in mind, you may see a flat voltage on these signal wires, and I've actually seen it on both the positive and the negative wire going to these sensors. Just keep in mind, the only reason it's there is to monitor circuit integrity, meaning that if I unplug that sensor or wire breaks or there's an open in the sensor, we'll set a circuit code for these sensors. All right. And although this is not always true, if you see a circuit code for one of these style sensors, it probably uses a bias voltage. Although, again, there's so many variables here. You can have a circuit code that where if you actually get into and read the definition, even though it says circuit in the definition of the code, it is actually pertaining to a loss of signal. And then so it's just inferring that there's a circuit problem. So I don't know, maybe I shouldn't even get into that because it kind of muddies the waters a little bit there. But anyways, just keep in mind, there may be DC constant, which is a bias voltage for circuit integrity. It is not used by the sensor itself in order to operate. These things can generate their own voltage, and they do. And the reason I want to bring that up is because the voltage that's produced on these sensors is actually an alternating current. So this would be alternating in polarity. And if we go back to imagining that magnetic field expanding and collapsing around the sensor, it makes sense why these things make an alternating current, right? So I kind of like to think of the sensor as a little battery almost, because again, it makes its own voltage, but different than a battery, right? If we just think of a normal battery, we have a positive and a negative output. Right? That just, it's direct current. It's always that way. These sensors will alternate the positive and the negative terminals, if you will. So it's generating its own voltage, but it's going to flip-flop in polarity as the magnetic field expands and collapses, right? We're moving the direction that the magnetic field moves through the coil of wire. We're changing that, right? So if you think of a coil of wire that's stationary, and we're expanding a magnetic field across it outwards, that's one direction. And now as the tooth moves away from the sensor, we're contracting, we're decreasing that magnetic field. It's moving through the conductor, again, going to be inducing a voltage, but in the opposite direction. Okay. So the direction that the magnetic field moves through the conductor changes the direction of current that's induced. Okay. And so we need to be aware of this because that is going to flip flop the polarity, right? So one end of that sensor will be positive at one point and the other negative. And then as that magnetic field changes direction, we flip flop. Now we have positive on the other side and negative on the other. And that will go back and forth as the teeth move past. And that's why we see an alternating current, or if you're to scope this, you see a sine wave. It's the up and down squiggly line. It's not a sharp digital signal. This is an AC waveform. Now, if you're scoping this, you don't necessarily have to use AC coupling. You definitely can. But if you're using a Pico, you can use DC and you can still view this waveform. But what you're going to see on the scope is you're going to see that this waveform goes above and below 0 volts, right? So 0 would be nothing. There's nothing there. You'll see it go negative, and then you'll see it go the opposite. You'll see it go positive, right? And again, that's because of how we have the scope hooked up to it, and that the polarity is reversing, right? I'll get more into the circuitry there and how we're connecting our scope setup in a little bit, but let me continue to talk about the sensor here. One thing to keep in mind as well is as the component is spinning, we're generating this voltage out of it. Obviously, as the component spins faster, we'll change the frequency of the pulses, and that's really what the computer is looking at, is these pulses to determine the speed and in some cases the position of the component. We increase the frequency, and that's pretty basic, right? As something spins faster and it's generating voltage pulses, you're going to generate more voltage pulses as that component spins faster. And again, that's fairly obvious. The other thing that, unless you've scoped or measured one of these sensors, you may not be aware of is the amplitude of the waveform also increases, meaning that the voltage level that is output from this sensor goes up significantly as the component rotates faster. Because the amount of current that's induced from a changing magnetic field not only just is dependent on the strength of the magnetic field, but also the speed of said magnetic field moving through the conductor, right? And so as we spin a component faster, we are changing the speed at which this magnetic field moves through the conductor. So the faster this thing gets, the more voltage that this produces. And I've scope some of these sensors, we're seeing 30, 40 volts out of one of these little sensors that it's generating. It's actually pretty impressive. I did do some reading, and that actually is a detriment to the sensor because at the higher voltages, there's more chance for electrical noise. And then the opposite's true as well. If we think that the voltage is going to go up as the component spins faster, the inverse is true. It's going to go down as the component spins slower, meaning that these sensors have poor performance at low rotational speed. All right. Now, for an engine, this isn't necessarily a problem. I mean, even at cranking, we're going 200-300 RPM, which is enough to make a signal. Where this can be an issue, and is an issue in some cases, is wheel speed sensors, right? So we can have a pretty slow rotating wheel, right? If we're in a parking lot, we're going 1 mile an hour. That's a pretty slow rotation. These sensors are actually pretty poor performance at slow rotational speed. Not that they can't be used, but they're not going to be extremely accurate at a slow rotational speed. Now, this is in comparison to a digital sensor like a Hall Effect or a Magneto resistive. Those can give information even at 0 rotational speed, right? Obviously, there's no movement, but they can still tell a computer, okay, I'm on a tooth or I'm not, even at 0 rotation. And again, that's just not the case with these sensors. So they do have a limitation to them, poor performance at low speeds. Here's the other thing, and this is also true of other sensors as well, but air gap is extremely important here. If we move the sensor away from its rotating component at all, we're going to have issues with the voltage that it produces, right? It's all based off of this magnetic field to determine how much voltage is produced, the amplitude that's produced. And some of the filtration, and I guess I didn't talk about this yet, there's circuitry within the computer that has to process the signal that's coming out of this sensor, right? Because this is an AC waveform, and computer processors, microchips, cannot utilize AC waveforms directly or analog signals directly. They have to have some filtration, and that's all built into the circuit board in order to process that signal into a digital input, right? On, off, square wave, if you think of it that way. It changes it from an analog signal, filters it to a digital signal. And within that, there's a threshold of voltage that it's looking for it to cross, right? So, for instance, if you look at a crank sensor in a lot of vehicles, that's a VR style sensor, it needs to be at least half of a volt of AC in order for the computer to register it as a viable signal, as movement of the crankshaft. And if it's below that point, it could still be outputting a voltage. Let's say it's putting, 0.2 volts out. Even though it's outputting a voltage, it doesn't cross the threshold in order for it to be counted as a signal. And that's where some of these sensors can fall short, when either the sensor becomes weak or there's an issue with an air gap. So a lot of you probably have dealt with this. I'm going to give you an example of where this happens. If you live in the Rust Belt or the North at all, you've seen this on GM trucks with ABS. The customer complaint is false ABS activation at slow parking lot speeds, right? So you come to a stop in a parking lot, and right before you hit a stop, the ABS kicks in, and it's a perfectly dry road. There's no slip. Your wheels aren't locking up, but the ABS kicks in. There's no codes either. This does not set any trouble codes. You just have this ABS activation when you come to a stop. Well, what's going on here? One sensor on one of the front wheels is actually being pushed up away from the tone wheel slightly. It's not much, but just a little bit from rust buildup. And these sensors on these wheel bearings, I'm sure you've changed one, only have one bolt, and it's a plastic sensor that sits on the wheel hub assembly. Well, the rust pushes this sensor up away from that tone wheel. And a lot of times it will be one sensor and not the other, or one will be more affected than the other. So what this does is, by moving that sensor away from the tone wheel ever so slightly, we reduce the amplitude of the signal, right? We're weakening that magnetic field. We're weakening the output of the sensor, and it will work at a higher rotational speed when the voltage output of the sensor is higher. But as we slow this sensor down, we actually reduce that amplitude to a point where it gets below the threshold for the module to count it as wheel rotation, right? The frequency is still the same. If you scope it, you can still see a voltage output. If you go right, left, okay, they're both outputting a voltage. If you were to count the little peaks, the voltage pulses, they're all there in the same frequency because the wheels are moving at the same speed, right? You can just come to a normal stop, and the speed of the wheels hasn't changed. The frequency of the pulses hasn't changed. But what happens is the one side that's pushed up away, the amplitude is dropped below that threshold point. The module basically considers that the wheel's not moving now. Okay. I don't see any pulses because we're not crossing that threshold, and it locks up. It says, okay, the ABS needs to be activated because we're in a skid. This wheel has locked up. The other one's still moving. We activate the ABS, and no trouble codes are set because that's normal. That would be if you were actually coming to a stop on an icy road and, one wheel locked up, it would activate the ABS and it wouldn't set a trouble code. And the fix for that was just to clean up the sensors. And a lot of time you have to replace them because they don't come out without damaging the sensor. We clean up the rust, and I found even if they're not perfect after the fact, like as far as equal amplitude, as long as it crosses the threshold, it's all good. Because again, the frequency remains the same regardless of the amplitude difference, but we can't have it drop below that threshold. Okay. And the same thing's true for crank sensors and stuff like that. If you have an air gap issue, especially at low rotating speeds, we can affect that minimum threshold that we need to see out of these sensors. So air gap is critical to these sensors, of course. All right, let's talk a little bit about testing for these sensors and what we can do. There's various ways that we can determine if these things are functioning properly. Of course, a lot of service information and codes is going to have you ohm check them. And not that you can't, because this is just a coil of wire and you can measure the resistance, and lots of them are, I'd say 1 to 2,000 ohms, but there's probably a bigger window than that. For the wheel speed sensors that I've measured in the past, they're somewhere around there. It doesn't tell you a whole lot except for maybe circuit integrity, right? Maybe you could go to the control module, find your 2 wires, ohm check it. If it ohm checks as something that you know is a known good, you could say, yeah, the circuit's intact, but that's really all you're getting from that. So it's a limited test. Not that you can't do it, but understand the limitations of that test. If you're going to bother doing it, it's not an end all be all test. It doesn't tell you if the sensor's actually outputting something. It doesn't tell you what the sensor's outputting. It just tells you, is the circuit intact? And even then, you're not loading the circuit. Not that this circuit handles a lot of current, but you could have an intermittent connection or a poor connection somewhere, and the ohm meter might not be able to tell you that's there. So anyways, that is one way that you may see a sensor be tested, is through an ohm meter. The other way you can do this, if you only have a meter, is you can switch your meter to AC output, go across the sensor, move whatever component needs to be moved, and you can measure the AC output, right? So like I mentioned, a lot of crankshaft sensors back in the day, you'd need to see a minimum of a 0.5 volt output. I can't say that's true for everything. And if we get into wheel speed sensors, camshaft sensors, and other rotational sensors, I don't have all those numbers. You might have to look to see if you can find it within the service information, if they offer it, or compare it to a known good. I can say I don't use my meter very often for these, but if that's all you have available to you, that is an option. That is one way that you can test these sensors. And some flow charts may have you do that as well. Now, the best way that I think to test these sensors by using a scope. And we mentioned the scope a little bit before. You can set it up on AC coupling or if it's Pico, you don't necessarily have to. You can put it on DC, and you can measure the signal out of these sensors, and you're going to see a sine wave. And there may be a missing tooth if it's a crankshaft sensor. So you see like a sync notch where there's no pulses. But otherwise, you'll see a nice up and down sine wave coming out of one of these sensors once it's operating. And a scope measurement is really good because you can see all the detail. You can see the amplitude, you can see the frequency, you can catch any glitches, right? Maybe there's a busted tooth on a tone wheel. Maybe there's just some issue with the sensor. Maybe there is an amplitude issue. You can catch all of that with a scope. So it's the best way to look at these sensors to see what they're outputting, because it's a dynamic sensor, right? We're measuring something that's moving, and we want to have a dynamic measurement to do it. And my preference here is using a scope and visualizing the pattern that's coming out of these sensors. Now, how do we hook up the scope in order to measure this signal? This is where there is some interesting things about this sensor, and actually kind of one of the reasons I want to talk about this is you'll see that these are a 2-wire sensor, right? We mentioned that. Now, not all speed and position sensors that are 2 wires are variable reluctance. Keep that in mind. And there are actually ones that have 3 wires, and Volkswagen comes to mind here. If you see those, these are still VR sensors, but they have a 3rd wire that acts as a ground shield. These sensors actually are susceptible to electromagnetic interference. You'll see, I should say, maybe not just the sensors, but the circuitry and the monitoring. They're susceptible to electromagnetic interference. So you'll see ground shields that are wrapped around these circuits. You'll also see a twisted wire pair in a lot of cases for the 2 wires that go to the sensor to reduce electromagnetic interference the same way that we would with a CAN bus circuit. So anyways, 2 wires to the sensor, sometimes a ground shield, but the wires that we're going to be testing are those 2. And if you look at most diagrams, you'll see something that says either signal or ground, or you'll see a plus or a minus. That's the other way. Now, usually the plus is going to be our signal wire, but it does get a little tricky there. So again, how do we hook the scope up? Well, one way that you could do it is you could just go across the 2 wires, right? So you could put, if you had your scope, imagine your scope lead, you're using channel A, you've got a colored end of that lead, and you've got a black lead on that end. You just go across the sensor. And that probably is the best way to go in most cases. But you could also put your ground part of your scope onto battery ground, and then take your scope lead and connect it to the signal wire. Now, which one do you connect to? I would connect it to the one that's listed as signal or positive, and that's generally where you're going to get a signal. Now, here's something that's a little bit interesting, though, is that if you run into a vehicle, I'm thinking of some right off the top of my head here, is a Ford or a Hyundai, and you have your scope set up like I mentioned, where the black part of your lead is connected to battery negative, and you connect to your signal wire and you see a pattern developed from this sensor. You can actually put it on the negative side and also see a signal. It'll be the inverse, but it'll look very, very similar to the other side. You'll see a signal on both sides. But if you go to Chevrolet or Toyota, for instance, and this may not be true of every model, you go on the signal wire and you see a signal, you go over to the other side, the negative side of that sensor, and you don't see a signal. That's completely normal. So what's going on there? This is a difference between a floating ground and a non-floating ground sensor. Now, the reason I want to talk about this is if you run into this, it's curious. It's like, well, why do I see a signal on both sides for one and just one on the other? It has to do with the circuitry in the control module. It's not the sensor. The sensor is actually doing the same thing. It is the exact, maybe not the exact same sensor, but functionality wise, it's the exact same sensor on both vehicles. It has to do with the circuitry in the ECM. And I've gone through and I've looked at some of this. It's pretty interesting stuff, but basically we're elevating the ground on a floating ground sensor. And this is used in a number of applications across the vehicle, like O2 sensors, on a lot of vehicles like Chryslers and things like that. But in this case, because the sensor is outputting an AC voltage, again, if we think of that bouncing back and forth, switching polarity, the positive side of that circuit switches back and forth on both applications. But on a non-floating ground, where one side of that coil is just connected to ground, we don't see it, again, if we're referencing battery negative. And all this is to say, the best way to connect to these sensors, maybe to not get confused about this, is to just go across the sensor. Okay, so you take your lead and you use sensor ground, if you will, and you're going to be looking for an output of the sensor. And that's probably the most efficient way, so you don't have to worry about any of this stuff, is to go across that sensor if you're going to be scoping it, or if you're going to be using your meter, or however you're going to measure the output of this sensor. Now, one thing to consider on this, if you're going to be using a scope that has multiple channels, okay, so imagine our crank sensor, and we have channel A, colored lead on the positive side of the sensor, black lead on the negative side of the sensor. And we're going to measure some other things while we're at it. We're going to look at a few other sensors on that vehicle because we want to see multiple inputs, right? Or maybe we're doing like a cam crank correlation or something like this. Now, you have channel B and you're connecting to, let's just say, an ignition coil, right? And you decide to take that black part of the lead for channel B and you connect it right to battery ground. What's going to happen is you're going to kill that engine, basically. You're going to disable that crankshaft sensor if it is a floating ground style sensor. And the reason being is, and I wasn't the one to figure this out. I learned this years ago through some other really smart people, is that the AC voltage can cross the capacitance within the scope, right? So you can kind of think of it as the grounds being shared within the scope, and we can actually ground out one side of the signal on the crankshaft sensor. So really all that's just to say, if you've got a floating ground sensor like a Ford, very common, and you're using multiple channels, just be aware you can actually disable that signal by connecting your scope that way. So it may be a rare situation to run into, but if you do, that's the reason why, is you're basically connecting ground to a signal wire through the scope as you're trying to test it. So something that can happen there, but kind of interesting that you can see a signal wire on both sides on some of these, but not all of them. And it all depends on the circuitry in the ECM, whether or not that's going to be present, floating ground or non-floating ground sensor. They're both out there. So that's going to do it for variable reluctance sensors. Not a whole lot more than that I wanted to cover, but hopefully that gets the basics for you and maybe a little bit more getting into that floating ground stuff. But other than that, let's all get out there, start fixing the world one car at a time.